This presentation is part of the TI-Focus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2018 AP Calculus exam, free response question AB2, namely displacement and total distance traveled. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start with a quick review of the Fundamental Theorem of Calculus Part 2 and present a practical interpretation that leads to the net change theorem. I'll talk about several applications of the net change theorem and some that we've seen on recent AP Calculus exams. And then I'll discuss in greater detail two important applications involving particle motion: displacement and total distance traveled. And finally, I'll present a couple of examples. The Fundamental Theorem of Calculus Part 2 says that if f is continuous on the interval a to b, and capital F is an antiderivative of f, then the integral from a to b of f of x dx is capital F of b minus capital F of a. Now, because capital F is an antiderivative of f, we can say, or we can write, capital F prime is equal to f. So the conclusion of the Fundamental Theorem of Calculus Part 2 can be rewritten as the integral from a to b of capital F prime is equal to capital F of b minus capital F of a. Now, we know that f prime of x represents the rate of change of y equal f of x with respect to x. And we know that f of b minus f of a is the change in y as x changes from a to b. But remember, y could, for example, increase, then decrease, then increase again. And therefore, f of b minus f of a really represents the net change in y. So, using this interpretation, we can restate the Fundamental Theorem of Calculus Part 2. I'll call this the net change theorem. The definite integral of a rate of change, say f prime, may be interpreted as the net change in the original function f. And I can write this mathematically or symbolically as the definite integral from a to b of f prime of x dx is equal to f of b minus f of a. Here's a closer look at this theorem. Another way to interpret this result is that the definite integral of f prime of x from a to b represents an accumulation in the change in f over the interval a to b. And we can also rearrange the terms in this equation to give us a practical approach for solving many AP Calculus type problems. We can write f of b is equal to f of a plus the integral from a to b of f prime of x dx. Or a way to think about this is that the end amount is equal to the start amount plus the net change. This principle has many uses, and it can be applied to rates of change in the natural and the social sciences. Here are some examples of the net change theorem in action. Let v prime of t represent the rate at which water flows into a reservoir at time t. Then v of t is the volume of water in the reservoir at time t, and the definite integral from t1 to t2 of v prime of t dt is v of t2 minus v of t1. And that's the net change in the amount of water in the reservoir between times t1 and t2. Suppose C of t is the concentration of the product of a chemical reaction at time t. Then the rate of reaction is the derivative C prime of t. And therefore, the definite integral from t1 to t2 of C prime of t dt is equal to C of t2 minus C of t1. And that's the change in the concentration of the chemical from time t1 to time t2. Here are a few more applications of the net change theorem. Let's suppose the mass of a rod measured from the left end to a point x is given by the function m of x. The linear density is m prime of x, traditionally labeled as rho of x. Therefore, the definite integral from a to b of rho of x dx is m of b minus m of a. And that represents the mass of the segment of the rod that lies between x equal a and x equal b. And here's a common application found on AP Calculus exams. Let's suppose that p prime of t represents the rate of growth of a population. Then the definite integral from t1 to t2 of p prime of t dt is p of t2 minus p of t1. And that represents the net change in population during the time period from t1 to t2. And this net change takes into account both births and deaths. The last application on this slide has to do with economics. Let's suppose that C of x is the cost of producing x units of a commodity. Then the marginal cost is the derivative, C prime of x. And therefore, the definite integral from x1 to x2 of C prime of x dx is C of x2 minus C of x1. And this represents the increase in cost when production is increased from x1 units to x2 units, or the net change in cost. Now, let's look at two important AP Calculus interpretations. First, if a particle moves along a horizontal line so that its position at time t is given by s of t, then its velocity v is equal to s prime. And the definite integral from t1 to t2 of v of t dt is s of t2 minus s of t1. And this definite integral represents the net change in position, or the displacement of the particle, over the time period from t1 to t2. Here's a closer look at this application. Now, if you're teaching AP Calculus, you probably already discussed this idea of displacement intuitively, especially when a particle is moving only in a positive direction. But this concept is really more general. This definite integral represents the net change in position of the particle over the time interval t1 to t2. The other important associated application involves total distance traveled by an object, or usually in AP Calculus a particle. So let's just think about this problem for a minute. If you want to find the total distance traveled by a particle over a time interval, then theoretically we have to consider separate intervals where the velocity is greater than or equal to 0, or where the particle is moving to the right, and where the velocity is less than or equal to 0, where the particle is moving to the left. However, we can simplify this process a little if we consider the absolute value of the velocity, the speed of the particle. Therefore, the definite integral from t1 to t2 of the absolute value of v of t dt is equal to the total distance traveled from time t1 to time t2. These concepts are nice in that we can visualize both of them. Displacement and total distance traveled can be interpreted in terms of areas under a velocity curve. So here's the graph of a velocity function. And I've labeled the area of 3 different regions, bounded by the graph and the horizontal or the t-axis. The displacement of the particle over the interval t1 to t2 is a1 minus a2 plus a3. And the total distance traveled by the particle on the same time interval is a1 plus a2 plus a3. Let's take a look at a typical problem involving displacement and total distance traveled. Suppose a particle moves along a horizontal line so that its velocity at time t is given by v of t. Find the displacement of the particle during the time interval 2 to 8. Find the total distance traveled by the particle during the same time interval. And if given the position of the particle at time t equal 2, sketch a graph of the position function. I'm going to solve parts A and B and leave part C for you. To find the displacement, we need to evaluate the definite integral of v of t from 2 to 8. And in this case, I can find a symbolic antiderivative. I'll evaluate at the upper bound, evaluate at the lower bound, and subtract. So the particle's net change in position over the time interval 2 to 8 is 162 meters to the right. In order to find the total distance traveled, we need to integrate the absolute value of v of t. Therefore, we need to find the intervals on which v of t is greater than or equal to 0 and those on which v of t is less than or equal to 0. So I factored v of t completely. And using a sign chart or some other method, we now have the intervals on which v of t is greater than or equal to 0 and those on which v of t is less than or equal to 0. So, to evaluate the definite integral, I need to split the original integral into 3 parts, and first evaluate the absolute value of v on each part. Again, we can find the symbolic antiderivative in each case here, and there's a little bit of arithmetic, but in the end, the particle travels a total distance of 178 meters over the time interval 2 to 8. Here's a technology solution to this problem and a graphical representation of displacement. Using the TI-Nspire, I first defined the function v. I evaluated this definite integral to find the displacement, and I evaluated this definite integral to find the total distance traveled. Here's a graph of the velocity function. The displacement is the sum of the areas of the regions above the horizontal axis, here 2 regions, minus the sum of the areas of the regions below the horizontal axis, here only 1 region. On the TI-Nspire, I used the Analyze Graph menu to compute the definite integral and to shade in the appropriate region. I think it's pretty cool that we can visualize this. And we got the same answer, thank goodness. Here's one more example that involves displacement, total distance traveled, and some other related AP Calculus concepts. And this example will require a greater use of technology. A particle moves along a horizontal axis so that its velocity at time t is given by v of t. Find the displacement of the particle during the time interval 1 to 10. Find the total distance traveled by the particle during the time interval 1 to 10. Suppose the position of the particle is x equal 2 at time t equals 0. Find the position of the particle at time t equals 6. Find the time at which the particle is farthest to the right and find its position at that time. Find the maximum velocity of the particle. Find the average speed of the particle over the time interval 3 to 8. And finally, sketch a graph of the position function. I hope this video provides some insight into displacement and total distance traveled, a few AP Calculus type problems, and the use of technology to solve and visualize these types of problems. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.